The normal distribution is probably the most powerful distribution. Let's start over. The normal distribution is the most powerful distribution that we have in all of probability. It arises in a whole lot of areas in typically the following kind of context, and that is that anytime you have a quantity that is a function of a sum. For instance, say the annual revenue of a business, where that's going to be equal to the sum of all the transactions that have happened over the year, either profits or losses on each one of those. Or say the total annual rainfall being the sum over 365 days of rain or not rain. Very useful in the civil engineering world. Or in, say, the manufacturing world, the deviations that you might have in the length of a machine part might be then the sum of a whole lot of variables, or you might even call them errors or deviations, such as those caused by temperature, humidity, vibrations going on in the process. You've got also, as you go along, tool wear, and that list goes on and on and on, that might create then the deviations in the length of the part that you're continually making. And here's one that will come up for us, and that is that a sample average is in itself a sum, right? I mean, we've all done a calculation of just a very simple average from a set of data, which is nothing more than taking of those n data points, adding them all up, and dividing by n. And so, particularly if n is large, then x bar is normal. And that's what's called a sampling distribution, and we'll get into a lot of detail about that in upcoming modules. Here, though, the big picture is that normal distribution does come at us in a whole variety of ways. Now, the other part of this that really gets us there, and it's a critical idea, and that is that it's the central limit theorem. That tells us that sums of numbers, quantities that are sums, lead to a normally distributed variable. There's a more elegant expression of this, articulation of this in your text and elsewhere, but the basic idea is still the same, that if you have any random quantity that's the sum of a whole bunch of other things, we have a lot of very good reasons to believe that that would be approximated by a normal distribution, or even theoretically becomes that. And sometimes that happens quite fast. It all sort of depends upon what the underlying probability distribution is on each one of the little individual random variables. For instance, if each one of these little guys here is exponentially distributed, or maybe it's uniformly distributed, but as we sum them up over time, time being here, the more of them we sum up, that the addition of all of those will tend to become the sample average. And two different people independently came up with this. De Moivre did this way back, about many years ago, many years before Gauss came up with this as well. And so two different people came up with this idea, and that's why you'll sometimes hear the normal distribution called the Gaussian distribution. Let's talk about the standard normal distribution. Before we go on to trying to apply it to a specific example, like our invest or not example that we had way back in our very first introductory lesson. Let's just get this basic kind of concept that's down here, because it turns out that the standard normal distribution in its various forms are going to be what we actually use for all those other situations. Right? The standard normal distribution is exactly that bell-shaped curve that you've probably seen in many, many different kinds of contexts. And the way I'm drawing it right now is with a very specific way, and we'll come back and annotate it and explain why here in just a little bit. But your peak of your bell is happening right where I put this vertical axis here. Right now, in the standard normal distribution, the variable name that we use is typically one of two, almost always. It's either z or it's the letter u. And what we have here, because it's a special distribution, instead of a f for the probability density function, we use the Greek symbol phi very often. Some people still use the f, but we like to differentiate it because it's so critical, such an important distribution, that we'll give it a separate name. So phi sub z of z, where z is the random variable, is a quantity. And in this particular standard normal distribution, it's centered here at exactly this mountaintop, and we're going to note that it is a symmetric distribution, so this peak right here in the middle is also the average, and it turns out for the standard normal that it's right there at 0. Right? By definition, we want it that way. Right? And it'll also turn out as a very critical value that the inflection point as we go from concave down to concave up is going to happen right exactly at 1 n minus 1. That'll turn out to mean to us two things. One, that we've got our mean is going to be 0 and our standard deviation is going to be exactly equal to 1. We do this as this standard so that we can rescale it or shift the curve around to meet our actual mean and our actual standard deviation that we have. Right, before we get into too many more properties of this curve, let's go back and formalize here what the functional expression is for the PDF. Right, and so our phi z of z is going to be equal to 1 over the square root of 2 pi e to the minus z squared over 2. Right? The z is up here in the numerator of the superscript, and it is squared, and it's all divided by 2 with a minus sign. Right? Note that the squaring operation is what gives us the symmetric shape, right? Because now it doesn't matter which side we're on, the negative gets, in a sense, canceled out here when we do the squaring operation. Right, and there's that little sort of an exponential-like decay that we get out in here as well. And the 1 over square root of 2 pi is just a scaling factor because, remember, the total area under the curve has to be equal to 1 to be a proper probability density function. Right? Our domain range for z as this continuous variable is from minus infinity to infinity. Right? Let's take a look before we go too much further about some basic properties and also about what this looks like from a cumulative distribution function standpoint. And remember, from cumulative distributions, we're talking about the likelihood that our random variable is less than or equal to something, right? The area to the left of any specific location. And that's given also a very special symbol, capital phi, and sometimes they don't put the little subscript here, sometimes they do, but the argument is z for a shorthand. Right? That is, in calculus terms, well, that's from minus infinity to z, and then I know that looks like a 3, but that's a script z, and that would be then 1 over the square root of 2 pi e to the minus, now we use a dummy variable, u squared divided by 2 du. Right? Well, that is not exactly a tractable equation to deal with. And so it turns out that what we end up using are actually tabulated values for the CDF of the normal distribution. In almost all practical situations, that's what we use. We don't actually evaluate that analytical expression ever. All tabulated values. And that's true whether it's in the computer or whether it's processed by hand, like I'll show you here in a second. Then it's all about the tabulated values. Right. Let's take a look at some of the critical properties, and we're going to redraw this distribution probably a number of times. So when we look at the critical properties, note that if we want the probability that our random variable is between two different random variables, there's a couple of different ways that we could actually play around with that. Let's go back and draw what it is that we're after here. Right, there's our normal distribution, bell-shaped curve, there's 0, and here's our, say, z2, and here's our z1, and so the area that I want is this. And I don't mean to imply at all that somehow z1 and z2 are somehow symmetric about 0. They're just two arbitrary numbers there. Right? Now, you could go and try to evaluate this thing in terms of finding the exact area. You could plot this to scale. You could graphically find this area. There's a lot of ways that you could ultimately do this. But probably the easier way to do it is the old clever trick you learned in a statics class, and that is to look at, in a sense, adding and subtracting areas. If we were to come out here and look up what the CDF is for Z2 and find that area, so that would be the probability that Z is less than or equal to Z2, then we could subtract then the area that's to the left of Z1. And in terms of the symbol that we just were working with before, and how you'll see this sometimes expressed, is that this will be capital phi, because that's the CDF, not the PDF, right, of Z2 minus capital phi of Z1. It'd be a very common way to take a look at that. Right. One more thing before we go on, and that's some critical typical values associated with the normal distribution. And again, we're just looking at the standard one, and the standard is absolutely by definition the one that is centered on 0 and has a standard deviation exactly of 1. And note that right here at this inflection point, 1, -1, that area that is in between is approximately 68%. And that number, a little bit more precisely, if you go take a look in your book on page 119, is 68.27%. If we go out a little bit further to -2 and 2, so that'd be ultimately 2 standard deviations, then the area between those is 95.45%. And actually, of course, in both cases, the digits go on infinitely long. And sometimes you're even interested in going out further than that. So far that we're off my little drawing already, right? -3, let's extend the axis out a little bit. Get way out here in what we call the tails. It gets skinnier and skinnier as we go out there. And now we're talking about 99.73%. Right? So if you have a normal distribution, then the chance that any one random quantity is within 3 standard deviations of the mean is going to be 99.73%. We're going to use that kind of notion quite a bit as we're going to develop some confidence intervals associated with a sample mean and asking the question, how close is the sample mean to the true mean of the population? Things like that. Those are confidence intervals. We'll use a similar kind of idea when we get into hypothesis testing and trying to decide, hey, is this process just the results we're seeing? Is it a part of just the normal randomness, or is there an actual systematic change in, say, the length that the machine is producing a particular part? Now, one of the nice things about the standard normal variable is how you can use it for other things. So let's look at a random variable x that we believe to be normal with a mean and a standard deviation that's not 0. Notice the probability notation here. We use the little tilde to say, hey, this random variable, and sometimes we use these big serifs or Roman numeral type of thing to indicate, hey, that's the definition of the random variable. That comes from the normal distribution, capital N, and then in parentheses we put a number for the mean and a number for the standard deviation. Right, in our case, let's go back to the example that we had from the very first lesson. That was the rate of return on an annual basis on a particular company investment. And we said, well, the mean was 10% annual return and the standard deviation was 15%. I'll put here in parentheses units are percent, but because we're often talking about probability, that gets a little confusing, and so I'm going to, one of those few times I'm going to leave off the units on the number because that can get real confusing real fast if you're not careful. Okay, so here we have that our rate of return is our random variable, right? And it's normally distributed with mean mu and standard deviation sigma. So how do we ask the kind of questions such as, well, what's the probability that in any given year that we have a loss? How the heck do we deal with that? And now we could have a table that would have all the infinite combinations of mu and sigma, but obviously that doesn't work. Instead, what we have is the standard normal tables. And there we define the standard normal variate to be z is equal to x minus the mean of x divided by the standard deviation of x. A lot of times people don't write the subscript of x down here. It's implied, but we're going to be talking about the mean and standard deviation of z here in a second, so that will be important. But note, this population parameter for x and standard deviation for x, those two population parameters are, quote, constants. So shifting things by just subtracting a constant from x and then rescaling it or normalizing it by the standard deviation of x is going to mean that z and x are going to have exactly the same kind of distribution. That is, whatever distribution x is, z will have the same. Now the individual values will be rescaled or shifted, but the big picture is that they have the same probability distribution. And we're going to show that ultimately here that the expected value of z is going to be exactly equal to 0. And we're going to do that by working with the expected value operator. All right, so we'll substitute in for our quality, and then, oh hey, you know, these are just constants, right? And we've got just a difference. It's a linear operator. So when we do that, we can pull out the constant here. We get the expected value of x minus, then the second term will be the expected value of mu x over sigma x. Those are constants, so that's just that. And g, expected value of x, is the mu of x. And so what do we have? We have 0. And that's your mean of z. When it comes to the variance of z, we get really ultimately something similar here, right? Variance of z is, ooh, this could kind of look a little ugly, right? But we could put in here, well, that's the variance of x minus mu x over sigma x. We could work at it from that standpoint, but its variance is not a linear operator, so that's, you know, let's not do it that way. Instead, let's go back and say, hey, the variance of z is the expected value of z subtracted from its mean quantity squared. And we happen to know that that's 0, right? So we could get rid of that right off the bat if we wanted to. And so that's just the expected value then simplified to expected value of z squared in this particular case, all because the mean of z was 0. Right? And then we can substitute in for z that we'll have x minus mean divided by sigma of x, that's squared, and now that becomes, oh well, we can factor out some things, right? 1 over sigma x squared, and then we can also recognize that, oh, wait a minute, that in itself is the variance of x, right? So probably should have written that in the top, because now it looks like those two are times each other, but it's not. It's that, and boom, that equals 1, and that is our variance for z. And of course it means the standard deviation for z is equal to 1. Right, so what we've just demonstrated there is that if x is a normal distributed variable with a mean and a sigma, then when we do this, what's called a standard transformation here for z, we're going to end up with that z is also normal with mean 0, standard deviation of 1. In other words, z is the standard normal variable that we've been talking about. Right? Oh, wait. You know, we were actually after this problem, this question of what's the probability of loss in any one year. So let's take a closer look at that. That's wrong.